Hello, I'm Doug Montgomery, and I would like to welcome you back to our first Fireside Chat of fall 2022. I wasn't aware of this, but I got a count a couple of minutes ago. This is Fireside Chat number 22. So we've been at this for a while, and hopefully you've either been here before or you've looked at some of the recordings of the Fireside Chats, which are on Coursera. For those of you that are sort of new to the party, either to the course or the Fireside Chat, this is something that we generally do every month during the academic year, my Fireside Chat always has a guest speaker, and we talk about specific topics of interest to the experimental design community. Sometimes we talk about applications, and we always try to leave some time at the end for questions. So if you have questions, this is a great time to sort of ask them, and you can put them into the chat. You don't have to wait until we get to the Q&A part of the Fireside Chat. You can type them into the chat feature in Zoom anytime you like. We try to answer them on air, but if we can't, then we'll take a look at answering those offline, and they'll get the answers will get back to you somehow. Okay, we always make sure that all the questions get answered. For those of you that are on Coursera, these are posted in Coursera. They're in the resources tab of your course. I'm pleased to have our guest today, Dr. Brad Jones, Brad is he's a repeat offender. He's been the guest before. And I'm really pleased that he could take the time out of his busy schedule to join us. Brad is the Distinguished Research Fellow in the JMP Statistical Discovery Division of SAS. He is very well known in the design of experiments community. He built the JMP Custom Designer in JMP. He has a patent on the use of experimental design in minimizing registration errors and manufacturing printed circuit boards, and about a dozen other patents for innovations in experimental design. If you interact with JMP at all, probably the thing that you see that I think he's most famous for in JMP is the prediction profiler plots that allow you to do interactive exploration of multiple input, multiple output response surfaces. This is just a really fabulous feature for helping you interpret the results of a design experiment. He's widely published. He's the co-developer with Chris Knoxheim of Definitive Screening Designs. They have a number of excellent papers on that important topic. With Peter Goose, he wrote Optimal Design of Experiments, a case study approach, won the 2012 Ziegel Prize. A great book. In fact, they're in the process of revising that book right now, he tells me, and so there'll be a new edition of that soon. And full disclosure here, Brad and I have also written a book together called Design of Experiments: A Modern Approach, which is essentially an introductory textbook on design, but all from the optimal design approach. Brad has been well recognized for his research work. He has won the Brumby Award from the American Society of Quality, 2009, 2011, 2022. Yeah, there's sort of a gap there, but that's all right. He's still hitting on all cylinders. He won the Lloyd Nelson Award from ASQ, 2010, 2012. That recognizes the article that has the greatest impact to practitioners. 2012, he won the Statistics in Chemistry Award from the ASA, and he's won the Uden Prize for the best expository paper in technometrics in 2012. He also received the William G. Hunter Award in 2021 and the Short Medal in 2022 from the ASQ. He's a former editor-in-chief of the Journal of Quality Technology, and he's a fellow of the American Statistical Association. So I'm really pleased to have him with us today. And Brett, I'm going to turn it over to you, and you've got the floor.
Okay, I'll share my screen. So you should see a PowerPoint presentation if
I do.
Wonderful. So what I'm planning to talk about today is computer experiments, which is different from the kinds of experiments that you do typically in industry. And so I'm going to introduce some concepts that are important for this particular topic and make some recommendations. And my slides are not advancing. There we go. Okay, so here's the outline. I'm going to start with a little introduction. I'm going to discuss some design types that are important in computer experiments, give you some examples, and then make recommendations. So I want to start with a comment that Jeff Wu, who's a major professor at Georgia Tech, and a very well-known author in design of experiments in his own right. I went to this conference in Nankai, China in 2006, and Jeff Wu started off his presentation there by saying physical experiments will be replaced by computer experiments. Well, I love that comment because I was just starting to make some algorithms for designing computer experiments in JMP. And so I loved hearing that, sort of made it clear that I was maybe on the right track. So let's compare computer experiments with physical experiments. Computer experiments are fast because you don't have to build any prototypes. You don't have to you don't have to set up a process. You don't have to run the process. You've got a computer model, and basically what you're going to do is try to probe that model to find out what the important effects are behind it. In a physical experiment, you have to build either prototypes if you're making things, or you have to run a process, and then at many different times. The cost of the prototypes could be very large, especially if you're trying to build something like a heat exchanger. But the thing about physical experiments, if you can perform them, is that they have empirical validity because you've actually experimented with the real process or the real thing that you're interested in. In a computer experiment, you don't know whether you've captured everything that's important about whatever it is that you're trying to simulate, because you're simulating. And so whether the simulator is good or not is always a question. And the best you can do is get a good model for probing the simulator. It doesn't tell you whether that simulator is predictive of the real world. But then you can compare predictions from the simulator with actual runs, and that's a way of validating it. So there are a bunch of applications of computer experiments. There's circuit simulation is often done in computer construction of printed circuits. So you want to know how those things are going to work. And there's a very powerful simulator called SPICE. If you want to do stress analysis using finite element analysis, that's another kind of computer simulation. There's a computer simulation that looks at the various aspects of a hurricane and can predict where that hurricane will go. Same thing for just general weather prediction. Those tools are getting better and better and have longer and longer reasonable outcomes of what might happen tomorrow. And then there's when you're looking at fluid flow through a channel or something like that, especially a channel that has obstacles, then there's a simulator called Fluent that can do a good job of that. So there are a bunch of different applications in a lot of different areas. You could also think about modeling things that you can't do in physical experiments, because you know, if you can't make people smoke 3 packs of cigarettes a day for 10 years and see what happens to them. It's just, it's not ethical.
Brad, to interrupt you, my example I always use of that is if you want to improve the waiting time in a hospital emergency room, it's kind of hard to reconfigure the emergency room and change the roles of all the nurses and physicians. I mean, you know, there's stuff you just can't do.
Right. So for that kind of thing, you would want to have some sort of queuing system model, and there are queuing systems simulators that would help with thinking about that. So good point. So how are computer experiments different from physical experiments? Well, the key and important thing is that in a computer experiment that doesn't have random noise added to it, or doesn't have a random number as a part of it, there's no random error. So if there's no random error, there's no point in doing replication, because if you run the same set of settings on a computer twice, you're going to get exactly the same results. And there's no point in randomizing, because what randomization is for is mainly controlling variance. So the other thing about computer experiments is that they're often very, the underlying model, the simulation model itself, may be quite complicated. And so the kinds of low order polynomial approximations that people generally do in physical experiments might not be adequate to deal with a highly complex underlying true model. In physical experiments, the kinds of designs that you may have heard of already are typically based on trying to minimize some version of variance, either variance of parameter estimates or variance of predicted responses. But since computer experiments don't experience variance, the designs that are focused on variance reduction are missing the point. So so that kind of means that we have to think about, okay, what do we want to do in order to deal with a computer experiment that doesn't experience variance? So the key difference in the computer experiments is that bias is essentially the only important consideration. And bias is the difference between your surrogate model, the model that you're fitting, given the simulation, and what the true function is that is behind the computer model. So the computer model is unknown to you before you do experimentation. You're going to create a model, and the difference between that model and the true function is going to always be due to bias, not variance. So you want a way of somehow dealing with bias. So when you have noise in a process, generally what you do is assume a fairly simple model, a model that has mainly first order effects, or maybe first order and second order effects. That's because, excuse me?
That wasn't us.
Are you able to hear me still?
Yes.
Okay. We assume the simple model when we have a lot of variance, because if you have a lot of variance, the variance is going to swamp out differences, small differences that are due to the bias between the true model and your more complicated model. That you can't identify the complicated model when you have a lot of noise. So then when you're trying to minimize variance, you spread the design points out away from each other, and that leads to factorial type designs, whether you create them using an optimal design algorithm or you use a predefined design, is still, it's all about making the points first far apart and then statistically independent of each other. On the other side of this, when you're trying to minimize bias, now you don't have any noise, and you believe that the underlying model may not be simple. So what do? Well, you try to cover the region with points, and that leads to the concept or the idea of a design that fills up space, whatever the space that you're interested in. So there are two primary alternative definitions of space filling. There's the maxi-min space filling design, and there's a mini-max space filling design. So in maxi-min, you're looking at design points and you want them to be far away from each other, but you don't want them to be on top of each other, because then you would have replication, which is not valuable. So you want every point to be some distance from other points in the design, and you want to looking at all the distances between pairs of points, you want to maximize the minimum distance between the two pairs that are closest together. So that's basically saying, let's spread our design points out as much as possible. The other concept is mini-max. So you want to minimize. Here you're thinking about, okay, I have an arbitrary point in space, and where is the closest design point? If I can minimize the maximum distance from any arbitrary point in space to the nearest design point, then I would have a mini-max design. Now, it turns out that solving that problem, getting a mini-max design, is very, very hard. But finding a maxi-min design is comparatively easy. In fact, there are things called sphere packing algorithms that exactly do that. So people tend to do stuff like maximize minimum distance because that's easy. The minimizing the maximum distance is so hard and would take so much time that people throw up their hands and say, well, I'm not going to do that. So there's some other considerations that are important, especially if you're going to do certain kinds of analysis. One consideration is, how does the design project to a lower dimension? Like if I were to have a 3-factor design, there are only 3 factors that were important in my simulator, my computer model. What if it turns out that one of those 3 factors isn't important? Well, then I would really only have 2 factors that are relevant, and you would just drop. You would smash the cube down onto a plane, and so what you want in that case is for the design in the plane to be as space filling just like the design in the cube was. So projecting the design should result in designs that are space filling, and in particular, they should result in a design that doesn't have replication. Suppose though there are certain design points that are not achievable. Suppose that you're in a cube, but you can't do all of the points in the cube because certain points don't make sense. Like you might have something where the space looks like this of things that you might do, and then these points over here were not feasible, and the points above here would not be feasible. You should be able to accommodate that. And so sometimes you also might have categorical factors, like you might have two different prototypes that are different enough that you can't describe them by any other way except to say this is prototype 1 and this is prototype 2. So you would like to be able to handle all of those things as well. So that brings me to the discussion of, okay, what kind of design types are people going to do? And so in interest of time, I'm only going to consider two different design types. One type of design is a Latin hypercube design, and the other kind of design is a fast flexible filling design. Both of these designs are supported in JMP. So if you have access to JMP, which I think you guys do, if you're at ASU, you can build any of these designs, either of these designs, using JMP. But JMP also supports a bunch of other space filling designs as well, which you could play with. So let me talk about Latin hypercube designs first. Latin hypercube designs were invented way back in the roughly 1979, when was the first paper that came out about them. And as a result, and they were the only choice for quite some time. So as a result, people started using Latin hypercube designs, and they became the most popular design because all the papers were written. Basically, people would say, well, we did a Latin hypercube design. And so it became so common that people didn't even consider other possibilities. And one nice thing about a Latin hypercube design is that no matter how you project the design down into lower dimensional spaces, they will not produce replication. The problem with Latin hypercube designs is that you can't easily accommodate constraints on the design space. You can't accommodate categorical factors except by doing some little tricks, but they're mostly, what you would have to do would be very ad hoc. And then a Latin hypercube design that has endpoints, there are n factorial different Latin hypercube designs. So now you have way more designs than you know what to do with, and you have to pick one of those designs. Well, I've already just talked about max and min as a criterion. So you could say, well, I want the Latin hypercube design that maximizes the distance, the minimum distance between design points. So that would be a way of sifting through the n factorial designs to find one. So here's one Latin hypercube design, and it's a very unfortunate one because it doesn't fill space at all. In fact, it confounds the effects of the two factors x1 and x2. So that would be one permutation of 1 to n. So x1 is going from 1 1 to 9, and x2 is going from 9 to 1. So they're both permutations of 1 to n, but very unuseful permutations. So let me talk about what I call triple F designs, fast flexible filling, because I can't say fast flexible filling more than once without making a mistake. So triple F is easier. One nice thing about them is that they can also guarantee that there will be no replication when they project down into a lower dimensional space. But the nice thing about them is that they can accommodate constraints on the space, either inequality constraints or even nonlinear constraints, and they can handle points that are infeasible, so you can eliminate those. And finally, they can also, in a natural way, handle categorical factors and discrete numeric factors. A discrete numeric factor is a factor that is numeric, but you can only, it's like if you had a click dial that only had certain number of settings, you go from the bottom to the top, there may be only 5 different settings that that factor could take from low to high. So that would be discrete. Whereas a continuous factor allows you to experiment anywhere between a low and a higher bound. So the con for triple F designs is that they were only invented maybe less than 10 years ago, and so they're not widely used at this point, but you can see that they're much more flexible and potentially more functional. Triple F designs also have the nice property that if you look, instead of looking for the minimum distance from an arbitrary point to a nearest design point, you could think about minimizing the average distance from any arbitrary point to the nearest design points. And if you could minimize that, that would be a little easier than minimizing the maximum distance. And in general, you're going to have better predictive capability if, on average, each design point is close to an area or a volume of space that's small. Triple F designs are also nearly orthogonal if the design space is not constrained. You don't have any replication and projection, which I already mentioned, and the design points are strictly inside the boundaries of the design region. So let me give you an example or two of both of these design types. So here's the maximum Latin hypercube design for 9 runs and 2 factors. And if you take a look at that, can you see my pointer?
Yeah.
Mm-hmm. Yes.
So this vertex and all this space here is not being covered. And the same thing is true over here and over here and over here. So there's a little question about how well you're going to be able to predict, in these areas of the space. And it looks very much like a 3 squared factorial design rotated a certain number of degrees. Well, that might be a good thing, but it might not, because if the design function underneath this didn't behave well, you wouldn't be able to discover what its true identity was. Here's a 50-run maximum Latin hypercube design in 3 factors. And look at this plot. This is the plot of x1 versus x3. And you can see that it basically lies on 4 lines in the space. And then in between the lines, there's just open space. So that doesn't feel all that space filling to me. This is X1 versus X2. That looks more space filling, but it's also very regular and doesn't have a feeling of you know, if the function didn't go exactly as you expect, this might not be good. And then if you look at correlations between factors, X1 and X3 are pretty highly correlated for a 50-run design. So all that to say is people have been using Latin hypercube designs, and particularly maximum Latin hypercube designs for several decades without really thinking very carefully about what exactly they're getting when they use them. So here's a triple F design, and I'm just illustrating here the fact that you can make one of these designs that fits on a torus. That you couldn't possibly make a Latin hypercube design that could do anything like that. In fact, I know of no other space filling design approach that would allow you to explore that. But you can imagine, wanting to do a design on locations in a tire where maybe you're interested in the stress at every point on the surface of the tire, and you might want to minimize that stress. Well, how are you going to choose the design points? This shows the average distance between an arbitrary point in space and a design point for both the triple F design and the Maximian Latin hypercube design. And in 2 dimensions, the two lines basically fall on top of each other. So there's no particular advantage to a triple F design if the space is perfectly unconstrained and you only have 2 factors. But as you increase the number of factors, the triple F design gets better and better in terms of minimizing the average distance between a design point and some arbitrary point in space. And this is an important consideration when you're doing modeling that is based on your hope that design points that are close to each other are also going to have responses that tend to be close to each other. For instance, sometimes there are nearest neighbor algorithms that are used for analysis, and that would be the kind of thing that you would want to use if you didn't want to specify any underlying model form. So I should spend a little time talking about the analysis of these things. The most popular analytical approach for computer experiments for many, many years, decades even, was the Gaussian process, which is also sometimes called a GASP or a GP model. And those models really depend on the design not having replicates, because when you if you have a replicate, this model can't be fit. It'll blow up. So the GASP or the GP model is a natural for using with the Latin hypercube design. So people typically, there have been maybe hundreds and hundreds of applications of people using Latin hypercube designs with Gaussian process models. Now, it doesn't mean though that's the best thing to do. It was just Those are the two tools they had. You know, when you have one tool and only one tool, that's typically what you tend to use. So I'm now to the point of my recommendations. I would say that if you have more than two factors and you have any kind of constraints at all, you would definitely want to use a triple F design compared to a Latin hypercube design. And what you should do in any kind you have data is there are lots of different modeling approaches out there. Gaussian process is one, but neural nets are another. Ordinary regression is a third. There are all kinds of machine learning models that are available now in all kinds of software. You should try multiple ways of looking at the data and inform yourself in that way. So now let me go over to JMP quickly and show you a couple of things in JMP. Here are my Latin hypercube design example. This is my unfortunate Latin hypercube design where x1 goes from 1 to 9 and x2 goes from 9 to 1. And if I do a graph builder of that, you can see that in one dimension, this is about as space filling as you can get. All the points are equally spaced from the nearest point. And then if I choose this, well, that's the same thing, but you know, now you can't tell the difference between the effect of x1 and x2. Of course, nobody's going to run that Latin hypercube design because it's clearly not maxi-min. But here's the maxi-min Latin hypercube design. I'll show you the same view. So again, here's x1, and and here's x2. So they both look exactly the same in one dimension. If I plot x1 versus x2, though, I get the picture that I showed you earlier in the presentation. And so just to show you how to build a Latin hypercube design in JMP, let me go to special purpose designs and space filling design. And suppose I have 4 continuous factors and I want to do maybe 50 points. Then here's my Latin hypercube design. And what people typically do is make a scatter plot matrix of the design points. So this is what the 2-dimensional projections of this design in 4 dimensions. And we could also look at the correlations of these. And the correlations don't look too bad. They're not much bigger than 0.05. So I wouldn't worry about this design too much since you've got quite a few points, and there's no clear preference in the direction that the points are taking you. So let me give you, so here's the triple F example. And here's a disallowed combination. So what I'm saying is the sum of the squared values of A and B have to be less than 0.5. they can't be less than 0.5 and they can't be greater than 1. So when you plot this, well, actually I can just run I have a graph builder script. This is the design that comes out. So I could create this using FFF. So I have 2 factors, and I want to use a disallowed combination script. And now I'm going to take this guy, copy it, and paste it in here. And then now the only choice, the only choice available to me is the FFF design, because none of these other design approaches can handle that. And it's not liking it. Oh, I think I have to do this. Okay, well, oh, yeah, the factors' names were supposed to be A and B, not X1 and X2. That could be a problem. Yeah, so here's and you can see this is a smoother, and it's showing that basically, the average of the point values at any point from -1 to +1 is almost constant, which is a good indication of the space filling nature of this here. I also wanted to show you just what happens with space filling design, and let's see, I want to do 4 continuous factors and FFF. Just to compare it to the Latin hypercube design. We can again look at the correlations of the factors. And I don't know if you remember, but there were a few. It's about the same as the Latin hypercube design. There are some correlations that are particularly small here. So the main value in using the FFF designs is their ability to handle all of these special cases that are difficult. Like constraints, categorical factors, and discrete numeric factors. Okay, that's all I planned for today. I'm willing to answer a question or two if there's time.
Brad, I think we have sufficient time to deal with questions. I wonder if any questions came in before the start of the fireside chat. Sometimes we get several that come in ahead of time, but it looks like we might have some that are already up in the chat. We'll take a look here. Okay, Brad, can you see these?
Yeah.
Yeah, can you give some tips on deciding the best methodology for our research? Boy, that's a that's a pretty broad question. I think for me to give any kind of intelligent answer to that, I'd have to know a lot more about the kind of research that you're doing. But as a general rule of thumb, I think there's very few research efforts that can't be enhanced by using well-designed experiments.
Yeah, so I'm seeing one question that asks, first a DOE to determine the interaction effect between A and B, where B is actually two factors clubbed together as a ratio. So that can be done, and it's a way of avoiding having to do mixture experiments.
Mm-hmm.
And it can be successful, and it can allow you to do what you would normally do in either a screening or response surface type situation. But you are assuming that that ratio is actually the thing that's guiding what's going on, more than the individual factor percentages themselves. And so that's the basic assumption underlying things, but it also makes the creation of the design easier. You don't have, yeah.
Brad, another problem that I've seen in situations like you're describing, where they're basically mixture components, is that the design in terms of the ratios doesn't fill the mixture space. It leaves portions of the mixture space unexplored, and
right.
And that can lead to unfortunate results when it comes to making predictions, because you may want to make predictions about how this thing behaves over the entire mixture space, and
right,
that's a problem.
Yes. So what you could do, if you are defining things in terms of ratios primarily, is once you've created a design, you can do the algebra to take those ratios and turn them into the unique values, and then you can look at the way the design looks like in the ingredients themselves, the individual ingredients.
Yeah.
And then if you don't like the shape of that, you could add points where you're seeing holes or missing areas of the design.
Yeah, augmentation. Yeah.
Yes.
Yeah.
But yeah, that's certainly true. If you're defining in terms of the ratios, you may not be able to cover the entire region of the individual factors.
Right.
But also in general, you're not going to want to look at single ingredient points a lot of the time anyway. Usually it's, if you're experimenting with mixtures, you actually want a mixture. You don't want to have pure components.
That's right.
So the second question there was DOE to determine interaction effect using only one run or condition with triplicates or repeats. That's like if you were doing a control chart and you're basically what you can do is calculate a mean and a standard deviation. And that may be a useful thing
Yeah.
to tell you where you are right now, but it's not really a design.
No, and it doesn't
So-
tell you anything about interaction or relationships between the factors. No.
That's definitely true.
Yeah, yeah.
So Doug also answered the question about, can you give some tips on deciding the best methodology for research? That's very much dependent on individual circumstances.
Yeah.
What's your budget? How complicated you think the underlying system is, and can you are there factors that are hard to change? Do you have constraints on what you
Right.
can run? All of those questions are important, and they would lead you in different directions.
That's true.
And then there's one final question that I see, which is about application area in textiles. Oh, I also see one more. Yeah.
Yeah.
North Carolina State has a whole textiles.
Yeah, it's a whole
faculty.
college of textile engineering.
Right, and they do a lot of experiments. The cool thing about design of experiments is that it's a very generic approach, and it can be applied to multiple different application areas. It's just important to think carefully about what things you want to try to understand in any particular case.
Yeah, Brett, I've seen lots of applications in the textile area. Looking at the strength of fiber, the quality properties of fabric. So there are a lot of applications in that domain for sure.
And this one by Christopher is a very interesting question. Is choice the best measure in consumer surveys to determine utilities, or can you use paired comparisons to determine how close a decision? Choice experiments are very useful, especially when you want to do more than just pairwise comparisons. You might have a whole set of possibilities that you want to consider, and you want to look at all of those possibilities. But if you paired comparisons is also a powerful way that is also simpler. So, but it does basically limit you to only looking at pairwise changes.
Brad, consumer choice experiments is a really interesting sort of subset of experimental design. And we don't really talk about it in the course, but it's a topic that would be of interest, I think, to people. And so I'm going to put you on the spot and ask you if you would be willing to come back and do a third guest shot on the Fireside Chat and talk about choice experiments sometime.
Yeah, well, as long as you say sometime, I'm willing to do that.
Yeah, well, we can negotiate a time. It doesn't have to. I know you're really busy, and you've got a book revision going on, and I'm in the middle of doing a book revision too. So I sympathize with you a lot. But I think that choice experiments would be an interesting topic for a Fireside Chat. And
yeah, well, a lot of my, I have multiple reviewed papers on the subject of choice experiments.
I know you do.
So I'm happy to talk about them because they were for many years, the thing I was most interested in.
I know,
I've moved-
and
I've
you did
moved
some of the
into
really
other-
innovative work in the area, and I know there's some capability to do this in JMP.
Yes.
I just don't have time in the course to get into it. So this would be a great thing to do for a fireside chat. So let's talk about it. We'll find a time to do it, and we'll let people know well in advance that the choice experiments is going to be a topic.
Okay.
And before we quit, I do have one question for you, for myself, and it has to do with sample sizing in these computer experiments. I recommend and I think this is actually written in the book, because I do have a section in one of the chapters that talks about computer experiments, but I give a rule of thumb that says that if you're running a computer experiment, you generally should have about 10 observations for every design factor. So if you have a 4-factor experiment, I would recommend about 40 runs. Is in your view, is this reasonable advice, or am I way off base with what I'm recommending?
There is a paper in Technometrics several years back where the authors actually took up that exact question. And they came down that the 10F rule works very well in some cases. And the basic case that we're thinking of is when the function isn't too wild, when it's when it's close to first order, or for first or second order, you're probably okay.
Reasonably well behaved.
Yeah, if it's reasonably well behaved, you're fine. If it's not, then you're toast.
Yeah, and I would be very careful about doing that if I had a lot more than 3 or 4 factors.
Well, I think you can think, if you have no noise, as you do in computer experiments, you don't have any trouble setting up the experiment. The logistics are simple, so you can accommodate more factors. And like in other types of experiments, you expect that many of the factors that you're simulating or are running through your computer simulation are going to turn out to be not important. So if you have some level of sparsity of effects, then you can have experiments that have 10 or 12 factors and not worry too much.
Brad, I appreciate your contributions today. We're running out of time. We like to stop right on time. So this wraps up today's sessions. We're going to continue on. We've got sessions planned the next couple of months. Be more information about that will be forthcoming. Thank everyone that joined today. We hope you see you again for future fireside chats. And by all means, go explore all of the ones that have been done before. All 22 of them are going to be in Coursera. So enjoy. And Brad, once again, thank you very much for taking time out of your super busy schedule.
It was my pleasure. Goodbye.
Bye-bye.